Hi, thanks for joining me. It's been a while since I've done an integral video, so let's just jump right in. We want to compute this integral here, the integral from 0 to 4 of log x, so the natural log of x, divided by the square root of 4x minus x squared dx. Okay, so if you want to have a go at evaluating this integral, pause the video now and give it a go for yourself, and I'm going to jump straight into a solution. Okay, so the way I want to evaluate this integral is do two different u substitutions and then get an equation involving I, and then from that deduce what I is, i.e. the value of this integral. Okay, the first thing I'm going to do though is just change this denominator here. It's currently the square root of 4x minus x squared, but we can just factor this guy here to give us x times 4 minus x. Oopsie daisy, like so. Now the first u substitution I want to do is a very simple one. Let's just have x equals u plus 2, so then that of course gives us that dx is equal to du, like so. Just plug it right into this integral. We're going to get the integral from, well, when x is 0 here, we're going to get that u has to be minus 2, and when x is 4, we can see that u has to be 2. Okay, log x is just log of u plus 2, and our denominator now is the square root of x, which is just u plus 2. And then 4 minus x is just 2 minus u. And the way to see that, if you want, is just take this equation here, multiply both sides by minus 1. So you get this. Then adding 4 to both sides gives us a 4 minus 2 here, which is just a plus 2, like so. And that's why we have 2 minus u is equal to 4 minus x. Okay, so we get this thing here, and of course dx is just du. So we get this integral here. But then this bottom we can see is just the difference of two squares. Or we can write it as the difference of two squares. It's just 2 squared minus u squared, which is 4 minus u squared, like so. Okay, so we've just expressed I in this way here. But I want to go one step further and just write this as the summation of two integrals. This is just integrating from 0 to 2 first of log u plus 2 divided by the square root of 4 minus u squared du, and then integrating from minus 2 to 0. So the integrand stays the same. We're just integrating from minus 2 to 0, and then 0 to 2, and adding them together, like so. Like so. And now if we just do a small substitution on this integral here, and just say v equals minus u, this integral here becomes the integral from, well, when u is minus 2, v is going to be minus 2, which is 2. And when u is 0, we can see that v is going to be minus 0, which is 0. The top log of u plus 2 is just log of 2 minus u. And then the denominator, square root of 4 minus u squared, is the same as the square root of 4 minus v squared. And then dv, of course, is just minus du, so du is minus dv. So we get a minus sign out the front, dv. But of course we can use this minus sign to switch the limits of integration. So this, get rid of that and then swap these two here. So we get now 2 on the top and 0 on the bottom. Okay, but of course we've still got to add on this previous integral here, which is the integral from 0 to 2 of log u plus 2 divided by square root of 4 minus u squared du. But hopefully you can notice now the limits of integration are the same, so we can bring everything under one integral. And what's even better is, this is supposed to be log 2 minus v. But of course it doesn't really matter, it's a dummy variable, so I can actually make all of these guys here u's if I wanted to, because the thing inside the integrand is just a dummy variable. And now bringing these under one integral, I can also see the denominators are the same, and so it's just log, the integral from 0 to 2 of log of u plus 2 plus log of 2 minus u, all divided by the square root of 4 minus u squared du. I would write it all out, but there's no space, but I'll bring it to the top of the whiteboard, and we'll continue with our second big u substitution in order to solve this integral. Okay, so we just showed that I can be expressed this way here. The integral from 0 to 2 of log of u plus 2 plus the log of 2 minus u divided by the square root of 4 minus u squared. We can go one step further though and bring the two logs into one log using log a plus log b equals log a times b. So this thing here, again, it will just be log of 2 plus u times 2 minus u, and that's the difference of two squares. So this thing here is just log of 2 squared minus u squared, which is log 4 minus u squared, like so. Cool, so that's one way we can write I, but now we're going to do a different substitution. We're going to say let x equal 4 minus u squared. Okay, or better still, we'll rearrange this just so there's no ambiguity in terms of plus or minuses. We're going to say let u equal the square root of 4 minus x. So here, of course, square root just means take the positive root. Okay, this, of course, rearranging will give us that x is equal to 4 minus u squared, and then that will give us that dx is just minus 2u du. Squeeze it on there. Okay, so let's plug that all into this integral here. We're going to then get that I is equal to the integral from, when x is 0, we can see that u is just the square root of 4, which is 2. And when x is 4, we're going to get 4 minus 4, which is 0. So u is the square root of 0, which is 0. Cool. Log x now is just log of 4 minus u squared. Okay, and the denominator is this guy here. So the square root of x, which is 4 minus u squared, times 4 minus x, but 4 minus x is just u squared. And then dx is just minus 2u du, like so. Okay, so there's a few things we can do here. Firstly, this minus sign I'm going to use to flip the limits of integration. So we get rid of this and then put a 0 here and a 2 here. Cool. This 2 I can also just bring out the front, like so. Now on the denominator we've got a square root of this 4 minus u squared times u squared, but of course the square root of u squared is just u, and that's going to cancel with this u we have on top. So I can get rid of this thing here and this thing here, and let me bring the du here, like so. And now if we hopefully just look at this, this might look a bit familiar because it's the same as this thing here, the thing we had that we showed just a second ago. But of course that equals I. So we have the I from before, which was this thing here we showed, is now equal to 2 times this integral here, which is also I. So we have the I is equal to 2i, and now this isn't a tremendously difficult equation to solve. This implies that I equals 0. Okay, so that tells us that the integral we initially had was 0, and that solves our problem. We've evaluated this integral. Now, you might wonder how on earth we're supposed to work out these substitutions, and the short answer is I don't really know, which is one of the reasons I was sort of a bit reluctant to make this video, because I like there to be a bit of intuition behind the maths that I show on the channel. But hopefully, though, this is at least exemplified that there's not always necessarily some nice intuition behind the types of substitution you use in order to deduce a result like this. Sometimes it does require a bit of luck. That being said, there may be some intuition here which maybe I haven't seen or I've overlooked. So if you know, or if there's a name for this sort of integral technique where you do 2 different u substitutions and you have to know the correct ones in order to get the right solution, if there's something like that, let me know, because I'd be very curious and I'd love to learn more about it. Anyway, thanks for watching. I'll catch you in the next one. Have a great day.